right, so we just talked about ideal gas law, right? So, DeBron, remind me what the first assumption is of the ideal gas law.
They take up no space.
Exactly, right? So ideal gases one, take up no space. Right? That means the volume of these particles of the gas are negligible, basically, right? Arshan, what's the second law? These molecules experience no
intermolecular forces.
Exactly. So no intermolecular forces. Another way of saying that is these molecules experience no attraction. They're not attracted to one another. They bounce together and they just collide off, right? There's no hydrogen bonding, etc., right? However, we're going to talk about real gases, right? So, DeBron, if I tell you something's ideal and something's real, are these two cases the same or are they opposite?
Opposite.
They're definitely opposite, right? So if they're opposite, right, that means these conditions are going to be opposite, right? So real gases then do take up space. So if these particles do have volume, right, an analogy is, let's say you fill a room full of people, right? You fill a room full of people, and they're crowded, they're very, we're all next to each other. There's going to be more or less space for the gas now?
Less.
Less, right? Let's take away the people, right? There's going to be more space for the gas, right? So, if these particles take up space, right, the volume of the gas in the ideal case, is it going to be larger or smaller than the volume of the gas in the real case?
Larger and ideal.
Yes, larger than ideal, right? So therefore, the volume of gas in ideal is greater than the volume of gas in the real. Okay? And why? Because basically there's less free space. Okay? So now let's think about intermolecular forces, right? So particles do experience intermolecular forces. So Arshan, can you tell me what's your favorite IMF?
My favorite IMF is hydrogen bonding.
Oh, wow. That's just... Why? Because of water, of course. Because of water, right? So, if IMFs do exist, such as hydrogen bonding, in, let's say, air, right? Because water evaporates and forms, vapor. So, hydrogen bonding does exist, right? So, what happens now? So, let's use the same analogy. Let's fill the room with people again. And they're all holding hands now. And they're all attracting each other, right? They're all pulling each other's hands, right? They're pulling on each other and they're coming closer to each other and further away from the wall, right? If they're going further away from the wall, there's less pressure on the wall, okay? If there's less pressure on the wall, that means when there are attractive forces present, there's less pressure, okay? So let's write it up here, right? So attraction of molecules what does that mean, DeBron? Less pressure or higher pressure than the ideal case?
So there's less pressure in the ideal case.
Yes, exactly. So the pressure of the gas in the ideal case is greater than the pressure of the gas in the real case. Okay? Great. So, just like the ideal gas law, right? These conditions can all be described by an equation, right? So, DeBron, remind me what the ideal gas law equation is.
It is PV equals nRT.
Exactly. PV equals nRT, right? But now we're talking about real gases, right? And real gases are described by the van der Waals equation. So, real gases are described by the, we'll call it the VDW equation. Okay? And so this is something you're going to have to be familiar with, but you shouldn't be intimidated by this when you see this on the MCAT. So first, let's look at the similarities. Arshan, what's similar about these two equations?
Pressure and volume.
Sure, we got pressure, we got volume, we got pressure, we got volume. But what about these sides? nRT. They're both
They're both the same.
They're both the same, exactly. So if they're both the same, right, we're now correcting for pressure and volume, just like we discussed over here, right? Pressure of the ideal case is different from pressure in the real case, and the volume of the ideal case is different from the real case, right? So in order to account for attractive forces and size of the molecule, right, we have to look at these terms, right? These are called corrective terms. So these corrective terms account for each of these things, right? So an squared over v squared accounts for attraction, and nb accounts for size. So what's a good way of remembering, you know, if an squared over v squared is attraction or size, or this one is attraction or size? So, DeBron, what word on this board here starts with the letter A?
Attraction.
Attraction, right, exactly. A for attraction. And therefore, B for size. So, Arshan, as let's say hydrogen bonding, your favorite IMF. Let's say if hydrogen bonding increases, right? What happens to A?
A will also increase.
Right. A increases as your IMF increases, okay? So, DeBron, what about size? What if my particles get smaller and smaller and smaller? What happens to B?
Decreases.
Decreases, right? So then, in the same way, we can say B increases as size increases, okay? So finally, let's talk about the conditions that give us an ideal gas and give us a real gas, right? So, okay, so in an ideal gas, do we want our particles close together where they can feel attraction, or far apart where they can be free and absent of attraction? DeBron, what do you think?
Further apart.
Further apart, right. The more further apart they are, the further apart they are, the less attractions they can experience, right? So does that mean, do we want high temperature or low temperature for ideal gases?
High temperature.
We want high temperature, right? So how did you know that, DeBron? What is temperature a measure of?
Kinetic energy.
Exactly, it's a measure of kinetic energy. That means they're moving fast and far and very fast away from each other. What about pressure, Arshan?
It would be lower.
Low pressure. So
Low pressure.
What gave you low?
They're opposite of one another.
That's okay. So that's a good way of remembering it, right? That's a good way of remembering. But let's think about being compressed and being uncompressed. If we want our molecules to be free in the ideal case, we want to be uncompressed, right? That's why we want low pressure, okay? So, DeBron, if we have the ideal cases taken care of, is the real gas going to be the same or opposite?
From the opposite.
Opposite, exactly. So in the real gas, we actually want low temperature and we want high pressure. Okay? That means we're forcing these molecules together. They're slow and we're squeezing them together. So we can experience more attractive forces. Okay? So any questions? All right, cool.